Okay, it is my pleasure to introduce our speaker today, Zachary Kingston. Zach is currently a PhD candidate at the Rice University in Houston, Texas. He works there in the lab of Lydia Kavraki. And to me personally, Zach is best known for having written the constraint-based planning framework in the open motion planning library, which basically allows us to use all the nice motion planning algorithms on constrained systems, which is of course super useful, for example, in grasping or locomotion. And Zach is also pretty successful. He currently holds a fellowship from the National Science Foundation and from the NASA Space Agency. He has authored and contributed to many open source software frameworks, most notably to MoveIt and OMPL. And he recently published the RoboFlex library, which is a benchmarking framework based on MoveIt. And Zach has done a lot of really nice work on multi-modal planning algorithms. And he's really, I guess, one of the experts on applying sampling-based approaches to motion problems, especially where contacts with the environment are required. And this will also be the topic of his talk today. And so I'm really looking forward to it. And I'm also very happy that he accepted our invitation. Here he is, Zachary Kingston.
Geez, man, thank you very much for the kind words.
You're welcome.
Well, yeah, hi everyone, and actually thanks for inviting me. It's an honor to be here. So hopefully going to keep this pretty casual. Stop me at any time if you have questions or you want to clarify anything. You know, like I said, want to kind of keep it, you know, try and get that in-person spirit a little bit. So yeah, like I said, so as Andreas introduced, this presentation is going to be an overview of my work on multimodal planning, which is really closely related to a lot of the stuff that you all do. So in my case, multimodal planning encapsulates like a really broad class of these interesting geometric manipulation planning problems. And I'm specifically looking at a class of problems that can be encoded with manifold constraints. And so, you know, as Andreas introduced, you know, talking about this manifold constraint planning framework in OMPL, I'll be talking about the details of that and how I'm leveraging that kind of down the line for these, you know, more broader manipulation planners, the multimodal planner, things like that. So this work is composed of those, you know, those ideas that all build on each other, you know, starting with how we find those feasible motion plans under manifold constraints, how we efficiently transition between different sets of these constraints, bias that search such that we can efficiently reach the goal, and, you know, actually all the software to tie all that together. But before I get into the work itself, let me talk a little bit about my motivation. Yep, I'm funded through a NASA fellowship. And as part of that, I've been working with a team down at NASA Johnson Space Center here in Houston, addressing the challenges that they specifically have for applying autonomous robotics in space. So to be specific, their use cases, you know, think about an astronaut on the ISS. What do you think they spend, like, you know, 50% of their time or so doing? Hold on, I just realized I'm not sharing my screen. Oh my goodness. I just went off to the races. All right, here we go.
We thought it was cool that you know, started off.
You know, everything's just an accident. All right, can everybody see my screen? Sorry about that.
Yes, perfect.
Awesome, great, okay. All right, well, here comes the cool video. All right, so if you guessed, what astronauts do most of their time doing is chores, like cleaning handrails, vacuuming, taking out the trash, all these kinds of, you know, logistics tasks, moving cargo bags around. Like, you know, you can see the 24 times speed up on this video. You can put yakety sax music over it and it would be very appropriate. So the idea here is, like, you know, why waste some of the time of the most highly trained people not on the planet when you could have something like a robot, you know, such as Robonaut 2 here, or R2 for short, you could have it do these tasks instead. So R2 is a dexterous humanoid-ish robot minus the legs that was designed as a prototype for these kind of in-vehicle operations, so inside the ISS. It can clamber across handrails, walk around, and theoretically it can mechanically do anything that you might want an astronaut to do. So R2 is also a really interesting case for motion planning because it is a high-dimensional system, it's humanoid, but we don't have to worry about gravity. So we can make a lot of simplifying geometric assumptions since we don't have to worry about things like dynamic stability. Moreover, so R2 lives in these really claustrophobic modules that are cluttered with all kinds of junk. You know, there's obstacles all lying around. And say we had, like, you know, some tasks that we wanted R2 to accomplish, like, you know, maybe like walk across the ISS, get from one side to the other. So you can see already that there's going to be a lot of challenges here in order to make that happen. So the first step of this problem is figuring out how we can even go and then reach another handrail. And so watch carefully. So here you can see that finding a feasible motion for R2 here, which is constrained to, not just keep its, leg end effector grasped to the handrail, it's also constrained to keep its waist upright facing forward because it's actually kind of a nice proxy for momentum constraints. The point of this is that solving for this problem requires solving for a motion plan in the presence of a manifold constraint. And so to this end, I'll be talking about that framework for manifold constraint sampling-based planning that Andreas talked about before. The way this framework works is that it decouples the way that these manifold constraints are actually handled from the planning, the search methodology, the way that some specific sampling-based planner explores or exploits the space. And this allows us to use specialized planners that are nice for high-dimensional systems, such as R2. So given that we can solve problems like this, the next question is actually how we choose which handrails to grasp and where on those handrails we can grasp. So there's a combinatorial number of options available. You can grasp any of the handrails around the ISS anywhere along their length. So does it go for a handrail nearby, or does it actually have some insight that would be a more effective choice in order to solve its goal? So to this end, I'll be talking about my multimodal planning algorithm that uses a layered planning approach that biases search towards feasible transitions. And this planner is informed on a line by successes and failures in both planning and trying to sample these transitions. So, now that we have this, obviously there's still a ton of motion planning that is going down under the hood, trying to find all these different feasible motions under each of these constraints. So the final idea here is how we can reuse prior experience in the context of that multimodal planner, such that we can accelerate that search, taking advantage of the fact that we're solving so many similar motion planning queries. So to summarize, the outline of things I'm going to talk about are, this manifold constrained sampling-based planning framework, the multimodal planner based on that has this, neat little online weighting scheme, an experience-based augmentation of that multimodal planning framework so that we can make it go faster. And finally, I'll talk a little bit at the end about the RoboFlex and kind of the software that I've been using in order to make this all happen. So pause here if you guys have any questions. If not, I'll just keep on going. Okay. So, I don't know how much I need to spend on this slide because you guys are all also motion planning experts. But, I want to introduce this little robot because I'm going to be using it as an example throughout the talk. So, we have a simple little planar robot, got 2 joints, alpha, beta. This robot has, can be represented as a point in some configuration space over here on the left. Typically sampling-based planning and planning in general, we just want to find some feasible trajectory. So, some curve inside the configuration space that corresponds to the valid motion of the robot. But in the case that I'm talking about before, we're not just concerned with obstacle-free planning. We also want the robot to interact with the environment, have things like contacts and constraints on its motion. And so we want to address the kind of the difficulties that come from trying to apply sampling-based planning in this context. So we model the interaction with the environment with these manifold constraints. So touching things, interacting with objects, maintaining contacts, all these things that are constant geometric relations in the workspace or the configuration space. All of these can be kind of encapsulated under the umbrella of manifold constraints. And so specifically, we model these as these multivariate functions of the robot's configuration that we want to satisfy. So here, in the example that I showed before, we have something like R2. Broadly, what this constraint might look like is that you have something that constrains the distance of the foot to some desired frame, and the waist of the robot maintaining that angle precisely of what you want. So, you can see that when this constraint function evaluates to 0, this constraint is satisfied. And, in practice, obviously there's some, numerical tolerance. If you have some small epsilon that you want to satisfy. But, the point of this is that when you actually define things mathematically as equal to 0 here, this actually induces this lower dimensional submanifold inside the configuration space. And what challenge this introduces is that this submanifold is of 0 volume with respect to the ambient configuration space, which gives challenges for the sampling procedure of finding valid configurations that satisfy this constraint, and also making connections between different points in the space such that free space motion no longer actually might lie upon this valid subspace. So help visualize this, consider this, this really abstract representation of some, arbitrary configuration space. This constraint function, it defines this lower dimensional manifold, this like, curved sheet or something, some lower dimensional structure inside the space. And this structure is not just, flat or like, let's say like a linear subspace or something like that. It can curve and twist with respect to the configuration space, but not arbitrarily, because in order for it to be a manifold, there are some, basic properties that it must satisfy. It has some continuity and differentiability. There's some nice properties that we can exploit in order to get guarantees out of the planner. So therefore, the problem that we're looking at here is in finding a path that lies onside or inside this manifold. All right. So to make this concrete, taking
Zach, can I ask a question?
Go for it.
Why is it just an equality constraint and not an inequality constraint?
Yeah, so you can do. So I'm specifically looking at the case of the equality constraint because specifically taking a look at the case because the equality constraint has this nice mathematical property of defining the manifold. In the case of the inequality constraint, you can get volumes in the space, and some of the math doesn't quite work out for some of the methods. So, I mean, obviously, kind of in practice, we're always looking at, inequality constraints of some form because we always have, maybe some volume that we want to have or some tolerance and things like that. And there's actually a lot of like interesting, the way that I want to put this is that I'm considering under the hood of this manifold constraint planning framework, there's two big methods that I'm using. There's, kind of, let's say, a simpler projection-based method, which is just, kind of doing this numerical, gradient descent, basically, of trying to find satisfying configurations with respect to the constraint function. But there's also this more complicated atlas-based method, which is doing this higher dimensional continuation structure building, where it's actually trying to approximate the underlying manifold of the space. And that kind of breaks down in the case of actual inequality constraints. And so in order for kind of the full unification of things, when I'm talking about it, I'm always talking about manifold constraints, which are only equality constraints. In practice, you could actually apply, the projection-based methods on the inequality constraints, but, you still get issues there with, kind of, density of samples on like the boundary of the volume versus inside and, all this kind of jazz. It's a super interesting problem. Definitely think they're relevant, but it's just, in the purposes of this work, only looking at manifolds.
Thanks.
So where was I? Oh yeah, example again. So, here's that simple manipulator I showed before. Let's put a constraint on it. So say we want to have that tiny robot's end effector move along a line parallel to the y-axis here. So you can see that that induces this submanifold in the configuration space shown on the left, visualized as this highlighted curve here. So it has a little bit of volume because, this is kind of visualizing the numerical tolerance here. So, with some small epsilon highlighted, once again, truly it's this, one-dimensional object in the 2D configuration space, but we're considering, with respect to some tolerance here. And it's also nice for visualization. So this is kind of the types of problems that we're kind of considering. And you can see here, it'd be in 2D, maybe you could sample from that with enough trials, but as you move into higher and higher dimensional spaces, the volume of that is basically zero with respect to the space. It becomes impossible to search for using sampling-based methods. So there's a ton of different work on how to solve, motion planning problems under these manifold constraints. There's, classical control methods, things like sequential convex optimization stuff, trajectory optimization methods, which I'm sure you guys are all very familiar with. There's also, kind of workarounds in sampling-based planning, where if you have an end effector constraint, you can just plan for the end effector in space with respect to that constraint, then try and use something like IK to figure out the resulting trajectory. Now, these are all, they work well for a lot of examples, but they all have the issues of them being these optimization-based approaches that are always going to approach some local minima, and they have troubles getting around kind of the global problems that I'm really interested in, where there's a ton of clutter or things that you need a really robust search algorithm for. So in this case, I'm taking a look at, the class sampling-based planning algorithms, which are, really nice for high dimensional, high cluttered environments, but they also require, like I was talking about, some additional consideration in order to be able to plan for that manifold constraint. So if you look at just kind of like, any old sampling-based planning algorithm here, just some, whatever your pick your favorite tree-based planning algorithm, RRT, EST, some acronym goes here. If you take a look at this, like you can kind of decompose this algorithm. Sampling-based planning algorithms are super modular in their structure. And all the smarts of that planning algorithm really kind of rely in, the selection step of choosing based upon your sample, where you want to extend from in your existing tree and where you're going to extend to. All the other properties of this planner, so how you're doing the sampling, how you're connecting different configurations, these aren't properties necessarily of the planner, these are properties of the space that you're having that planner operate in. Now, in the literature, manifold constrained sampling-based planners that have been proposed always required the design of some specialized planning algorithm. And so here you can see kind of a sketch of what that might look like. And really what these all do is they take the framework of some existing basic planning algorithm, typically something like RRT Connect, because that is kind of the de jure, whatever you're, if you have a planning algorithm or you have a planning problem, use RRT Connect on it. But with some modified components in order to address these issues of how you're doing the sampling and how you're doing the connection of different points in this tree. And so the fact that, these planners all have this kind of same high level structure, just modified in some small way, kind of leads to the insight that for the first contribution, which is given that you might have, here on the left, you have, just a regular old planning algorithm in the configuration space. And over there, you have a constrained planning algorithm that has that constraint function knowledge, planning on top of some configuration space. The contribution here, and watch the right, is moving that knowledge of the constraint function, where it's trying to actually exploit, or not exploit, but, address the issues of planning under this manifold constraint from the planner into the representation of the space so that you can have any old planning algorithm work with any representation that you want of these underlying manifold constraints. And so this decouples the way that the manifold constraint is satisfied with how the planner is doing search. Now, this is really nice for a couple of reasons, one of which is this allows us to kind of address broadly theoretical guarantees about these planners, so we can have maintained probabilistic completeness and asymptotic optimality properties of the overlying planner and tops of these space. And also, it allows us to find better combinations of motion planning methodology and constraint satisfaction methodology than those were prior proposed in the research. So let me make this a little bit more specific. So here's an example environment. So here's a sphere environment, which is this two-dimensional manifold that's embedded in R3. And being visualized here are a couple of runs of some asymptotically optimal motion planners to illustrate what this planning problem is. So, traversing the sphere, dodging obstacles, going from the South Pole to the North Pole here. And these are RRT star, bit star, and spars, I think, from left to right with different methodologies. Not going to go into the details here. But the important part is that in this environment, and here visualized are timing results for 100 runs of each combination of planner and methodology here. Not going to go into all the acronyms or the methodologies, but the important component here is on the right, where you can see that RRT Connect performs the worst out of all of these different planners in this environment. And recall what I said earlier was that these prior methods like C by RRT2, Atlas RRT, a bunch of different methods that I proposed in the literature are all extensions to RRT Connect. They're all based around this general search strategy. And so, this kind of shows that this decoupling is actually beneficial if we can, figure out, if you have a problem that you want to optimize your performance for, you can choose which things are going to work best for your specific problem. And this also enables us to handle use specialized planners that handle really high dimensional systems super well, such as, something like K-piece. So here's like a super complex system. It has 8 chains, each with, 7 links in the sequence, each constrained to lift this little disk at the end. And the way the system's parameterized is that each little blue ball is a point in R3, and the links are actually manifold constraints. It's saying that you have to maintain constant distance to your prior ball in the sequence. And so you have this 168 DOF system with 69 total different, let's say dimensions of constraint, and we can actually solve for this problem using specialized planners for this approach, something that, something like RRT Connect can never handle. And so I'll just let the video play out because it's, I don't know, Andreas, you also have a weird tentacle robot, I think, in your multi-level work, right?
Yeah, that's true.
That's that's all we're moving towards for motion planning, just more arms. Yeah, and so finally, to conclude this talk, this framework is available in OMPL, open source. Take a look. It's, I think, fairly well documented. I have a couple of tutorials and examples that walk through, and all the demos that I showed here, all available as scripts that you can run yourself. So yeah, take a look if you ever have a planning problem with these kinds of constraints. So before moving on, I'm going to pause if you guys have anything you guys want to talk about.
Actually, yes, I'd have a question.
Yeah,
I'm almost feel sorry. So maybe I missed the main part. So how was this in like the general framework that could, so that it could use any underlying planner inside? I just missed that. So
yeah. So,
you had this one slide only, right? Which was this one slide where you said that the configuration space. Yeah.
So I don't think I didn't really go. I skimmed over a ton of the details here. So definitely this is on the way that I'm presenting it. But the component here is really just replacing the underlying. If you take a look at this slide before, the underlying primitives that, or basically every operation that the planner uses that calls out to the, or really should call out to what would be represented as the space it's planning in. So things where you're trying to say, I'd like to connect 2 points in this space. That's now replaced not with a custom constraint solving thing that generates a geodesic on the manifold. That's just replaced with a call to the abstract representation of the underlying configuration space. So when you have these planners, like I said, very modularly designed, you have something like, underlying implementation of RRT. It's just going to call sample some point, extend some certain distance along what really is saying the underlying geodesic in the space that it's planning in, some small bit.
But that's a bit the point. So if I take here, so a constraint sample, does this mean that you already want to have a sample on the constraint manifold?
Yeah, so some planners, such as like PRM, are going to require the sampler to be able to generate samples that exist on the manifold. They can't.
But that's a problem in itself, right?
Yes,
like
it
a hard
is.
computational problem.
Yes,
and
yes.
So how do you solve that?
Yeah, so there's two methods that are implemented for representations of the underlying space. So there's one where it's just the kind of the bog stupid. You're taking a sample inside of the configuration space just randomly, and then you're using some numerical method in order to find or solve for a root of the constraint equation to project it using something like gradient descent. There's also these this atlas-based method, which is really a high-dimensional continuation approach, where as the planner explores along the manifold, it builds a representation of the atlas of that manifold by these linear chart representations. So it's building this piecewise linear decomposition of the manifold as it's planning. And that is completely, all that procedure of building that atlas and that approximation is in the space representation. The planner doesn't need to know anything about that.
Yeah, okay, I get that. And then I guess for the extend, so this line where it says constraint extend, how would you do that if you don't have an atlas? Don't you always also need, again, like a projection method?
Yeah, so the way that the projection method works in the case of the extension step is that given that some target point that you want to go to from some initial point, you make a small interpolation based on some hyperparameter and then reproject and do tiny steps along the manifold, constantly trying to extend towards your desired point. And so obviously you're going to run into issues here of getting caught in a local minima as you're making extensions. Not every connection is going to work. It's definitely has these issues. But the nice thing is that you can prove that there's always going to be able to make some amount of extension forward. It's never going to get fully trapped in any spot. If you have a point on the manifold, there's always some positive volume around it in which it can extend to its neighbors due to, like I said, nice properties, the fact that we're on this manifold.
So in summary, then you do everything as you usually do it, but you project everything.
In the case of the projection method, basically, yes.
Yes.
Okay. And that's like I said, so that's like, there's C by RRT2, there's the work, I think Mike Stillman's original projection-based planner, which was based on some like randomized gradient descent planner. There's a bunch of different ways. Projection is definitely the simplest way of handling everything, but yes, I mean, I would say that this is just one possible method that you can do. There's also variants on the atlas-based method where instead you just build a chart at one point and then use that chart. Like you don't actually build the atlas, you just use the local tangent space approximations for every single time you're trying to do an extension, something like this. There's a bunch of different ways you can handle the underlying extension, whatever approach you want to use.
Okay. And in the results you just showed, where you compared all kinds of underlying planners, like
Yes.
PRM and RT and so forth, have you used the same like higher level technique, like maybe projection, and then used all these underlying planners?
Yeah. So you can see here that like, so each of the, so every planner I'm running, there's 3 different versions of the underlying constraint solving.
Oh yeah, that's
work.
yeah. Mm-hmm.
Yeah. So
Okay.
this is the full like cross spread of every combination you could have.
Okay. Thanks.
Is there maybe just because I was taken by surprise, is there an easy explanation why, or an intuitive explanation why RT connector is so much worse than RRT, which
because it's constantly trying to
counterintuitive? Okay.
Yeah. Trying to make the connection. RRT kind of, yeah.
Is that more? It seems to look more an issue, like less an issue of the embedded manifold and more an issue of the specific object configuration, though. Right?
Yeah, I mean, and that's definitely, and that's the entire point about this is that, like, you know, the fact that we can solve these problems that have these manifold constraints that still have interesting obstacle arrangements that make it so that these different planning problem or different planners have different strengths, right? So in the case of by EST here, EST doesn't have something like the Voronoi bias that RRT Connect does. It has this neighborhood bias where it's just expanding based on the neighbors of the search tree, which works really well to rapidly expand across the space in this case.
Yeah.
And yeah, no problem.
I have another question.
Go for it.
So for planners like EST or the K-piece, I think they also internally use some projection method in order to do the KD query efficiently.
Yes.
So can you kind of combine that projection with the manifold projection?
So I've definitely thought about it because it'd be super neat to have something like the underlying, you know, like I said, the K-piece or EST, the like the coverage estimate projection that it's using, have that be related to the structure that you're building with the atlas, like this piecewise linear decomposition. It has the same properties, like you have these, you know, these linear cells that have the connections that, you know, are connected to each other. You could use that as something like that to inform the search. Totally interesting. Haven't done anything with it, but yes, you're definitely right. That it's something I thought about, but just never got around to. So. Okay, in the interest of time, I'm going to try and cruise along. All right, so multimodal planning. So, you know, we don't just have one manifold constraint, we have a ton. So consider, you know, R2 grasping that handrail again. You know, a single manifold constraint here corresponds to a single specific grasp of a handrail. So in the context of multimodal planning, we're going to call that single manifold constraint a mode of the system. And in the case of the multimodal planning problem, we don't just have this one constraint and mode that we're talking about. We're talking about, you know, R2 that can grasp the handrail, you know, anywhere along the length of this handrail, anywhere that you could possibly have it. And what's also interesting is that each of these constraints is similar. And moreover, the way that these constraints are parameterized are such that you could think about, you know, that grasp location as a parameter that then defines this family of constraints that could be imposed on the system. And so the way that we're modeling this is that the collection of all these different grasps is modeled by this foliated manifold, which you can think of as like a stack of these related manifolds. It's like a book where every single page is a manifold, and the page number is that parameter from the transverse manifold or that set of parameters. And so we're going to use a mode family as, or we're going to use a foliated manifold as a mode family as our collection of modes. So we have this, you know, parameterization where each parameter corresponds to a specific leaf manifold of that foliation. And every leaf manifold is defined by some sort of constraint function, and that is, you know, a particular mode. Yes, sorry, forgot that. Okay, so once again, visualizing this. So here's a really simple foliation in this abstract configuration space. It's got a one-dimensional transverse. So this, you know, kind of the line through space where every parameter on that transverse corresponds to some 2D leaf manifold. So here, this is the 1D transverse. It's like the spine. It's a line parameterized that you could say from like 0 to 1 or something like that, where 0 is one end, 1's the other. You can kind of see how this might map to, like, you know, a grasp on the handrail. And like I said, at every parameter on that transverse, there's a leaf manifold, and here those leaf manifolds are these like two-dimensional disks attached at every point. So you have then, given that you have all these leaves, each of them disjoint defined by the parameters on this transverse, that altogether creates that foliated manifold that we're considering. And this is the, this is the full set of every possible grasp that you could have on a specific handrail, something like that. So
if you ask something, sorry to interrupt. In the picture you showed before, like the family of submanifolds together had finite volume. But now in the handrail example, for example, you would have like a 3-dimensional constraint if you like fixed the grasp, and so the family of manifolds would still be like have 2 dimensions less, let's say, than the full configuration space, right?
Yeah. So you could have what's the way to put this? The foliated manifold is itself a manifold in the configuration space. But you can think of it as like, it's kind of the cross of these submanifolds, so, taking once again, like a specific grasp constraint, right? Like that is itself some submanifold in the configuration space of lower dimensionality. There's also a cross dimension, which is this parameterization, right? So that's the grasp location.
Yeah, I guess I guess my question was, so like in the handrail example, the volume of this combined manifold of all these grasps would still be 0, right?
It could be.
Okay.
Yes.
Yeah. Okay.
Not necessarily. It's just
depending on
what the dimensionality of your constraint, like of a single mode or leaf is, and the dimensionality of your parameter space, because it doesn't necessarily have to be a one-dimensional parameter space. It doesn't even have to be Euclidean. I'm just doing these Euclidean lines for simplicity's sake.
Okay.
It could be really any other. The transverse parameter could be any other submanifold in the space. And I mean, also there's I'm for simplifying things here, I'm talking about like, these foliations that all have these nice geometric intuition in the workspace. That's also not necessarily the case always. And so, the foliation is actually a structure in the configuration space. All the, the intuition with it corresponding to a location on the handrail is just, a nice mapping for us to help understand.
All right, thanks.
Yeah.
So it's one, sorry to interrupt.
No, go for it. Yeah.
So is one interpretation of the foliation now that it is actually an inequality constraint?
It could, depending on the volume. So in the case of so I'm going to show one here where it is going to be an inequality constraint, where it defines a space, like the total foliated manifold is itself 2-dimensional inside the 2D configuration space.
Right.
So that could be the case.
But not always.
But not always.
Okay.
Yes. So like, for example, here you could imagine that rather than the thing that I'm about to show, you could have it so that the line is itself a foliated manifold of point manifold or point constraints, where your end effector is fixed to remain at a specific point. So then you would have the total foliated manifold just be the ring here that you're seeing in the configuration space, that one-dimensional manifold. That's something that would also be a foliated manifold. Okay. Maybe got a little away from it. Hopefully that wasn't too confusing. Want to see if this helps people if they have any other questions. So once again, here's the simple manipulator that we had before. So one constraint defines that submanifold here, line along the x-axis. So here, let's say that height of that line's parameterized of, its height away from the x-axis here. So, here's a couple of different leaves. They all look pretty similar. Like, the constraint, you can kind of see that there's maybe some continuity here, and the image didn't load. Isn't that fun? Ugh, come on. Okay. There we go. Okay. Ugh, sorry about this, guys. Okay. Yeah, I think it's working again. Can you guys see it?
I can see something, but maybe you need to explain it.
All right. So, okay. So
Yeah.
you should see on the, so this is like the set of the, basically this is a visualization of the foliation itself, where the color of the foliation is corresponding, or, you know, there's a mapping from the color in the configuration space to the color in the workspace here. So you can see that as, you know, the parameter increases here, so you can see the kind of the gradient of the color in workspace corresponding to the line that the end effector was constrained on. That then maps to, you know, a, you know, kind of the identical color inside the configuration space here. And so this structure, this, like, you know, this 2D structure here that has, you know, a little bit of volume, things like this, it's the union of all the different underlying constraint manifolds that exist for this specific foliation. So this is, you know, this is actually what this would look like in this case. Is that clear for everybody?
Yeah, definitely.
Okay. So, you know, we're not just, you know, this is multimodal, not just single mode family. We don't just have one of these mode families, we have multiple. Here, R2 can grab either handrail. So, you know, we can transition to that other handrail. We can't just stay inside that one mode family. So we have to be able to explore the space in order to find that valid multimodal plan of finding transitions from when you're in a mode from one mode family to some other mode inside of another mode family. And also, as I was talking about before, if you want to switch between different modes inside the same mode family, you can't, because by definition, these leaf manifolds are disjoint. You have to do some transition in between things. This is kind of corresponding to, you know, no in-hand grasps functionally. If I want to grasp it, I have to re-grasp in some form. Yeah, so like I said, multimodal planning requires, you know, finding some sequence of these modes and transitions. And the way that we kind of capture what things can happen is with this transition graph. So here we have 4 modes corresponding to R2 grasping either one of these handrails in this example with either leg. This transition graph captures, you know, that important discrete structure that's present in multimodal planning problems. I mean, obviously the issue is with any of these types of problems where you have this structure, this can grow combinatorially in size as you have more mode families and more modes of interaction inside your environment. And if you're familiar with, you know, something like PDDL modeling of these domains, this transition graph is actually representing all the different, there's a mapping from this to the map, or to the, let's say the implicit graph that is of all valid action transitions. So every node here in this transition graph would correspond to some symbolic state, some set of predicates that are true. And then an edge would exist between these different nodes if there's an action that has its preconditions satisfied to transition between. So you can kind of see there the mapping between something like this to something with, you know, like I said, PDDL definitions of these domains. And so, you know, one thing I would like to do in the future is kind of extending this approach to those more complicated domains. But for now, we're just dealing with these fixed transition graphs. So back to this abstract example, let's add another foliation in so we can talk about multimodal planning. So we have to plan on one leaf at a time. And we, like I said, we can't move between leaves in the same foliation. These multimodal plans are going to move along leaves of a foliation, trying to transition to the intersection of leaves from different mode families, and then finding, you know, some path that exists on these different leaves on different mode families, transitioning in between them to eventually reach the goal. So that is the multimodal planning problem. That's what we're trying to solve. Any questions about this? So there's been a lot of work on solving problems with this multimodal structure, you know, which I'm sure that you're all very familiar with. You guys do a lot of work in kind of this space of, you know, doing transitions, blah, blah, blah. But here I'm organizing them very broadly into 2 categories based on how each approach deals with the integration of this discrete element, in this case, the transition graph, and how that relates to the continuous element, which is, you know, actually solving these motion planning problems. So in broad strokes, the way I'm doing this is that I'm going to call task and motion planning approaches that use a very explicit hierarchy between these layers. You have something typically that does like solving a discrete plan, some sequence of transitions, and then you try to resolve each of those transitions with motion planning in sequence. This allows them to get away with being able to solve really complex symbolic problems like block stacking, tabletop manipulation, rearrangement with a ton of objects, things like that. But they're much harder pressed when faced with complex geometric issues, because it's really difficult for geometric insight to be fed back into the discrete planner that's actually generating these candidate transitions. So if you have things where it's like, a tabletop rearrangement problem, but there's a ton of obstacles around, it's typically very hard to be able to have that information fed in some way that's understandable to the discrete planner. So that's a limitation of these approaches. On the other hand, there are what I'm calling multimodal planners, or integrated task motion planners, is used a couple times in the literature as well, because these are a more holistic approach of integrating the discrete into the continuous problems together. Now, the benefit of these is that they can handle a lot of the complex geometry issues that you might find. So, getting through narrow passages, dealing with intricate handoffs and things that require, a lot of geometric intuition for the problem. But they're typically not as efficient as these task and motion planning problems because they don't have the ability to have that insight of the total symbolic structure that they need to, explore. So one symbolic work, or one seminal work, sorry, in multimodal planning was by Chris Hauser, which presented this probabilistically complete approach to multimodal planning. So the details of the pseudocode aren't terribly important. This is a really simple representation. The important fact is that this planner is guided by a sequence of candidate mode transitions given in that extend tree function there on the left. And so what this function does is that it somehow selects an existing transition point in this exploration tree, usually through something like an RRT, like Voronoi bias criteria, and then finds or decides on doing some additional transition from the given point that we have in the tree to some new transition point, basically by using a utility table that was computed offline to decide what transitions are going to be good if you're in a specific point. Moreover, this approach used specialized samplers and planners for every mode family, and that is still really common in a lot of approaches of having specialized planners for every possible arrangement of the scene that you could have. Okay. So the inside of this work is recall that we have this underlying discrete structure, the transition graph. And there's been a lot of work in layered planning approaches, Andreas, your multi-level planning work, where you're exploiting reasoning in some simpler space in order to guide a more complete search. And so one example of this that does an interaction between a discrete abstraction and a continuous abstraction or a continuous plan is cyclop, this work cited here, that in this case was doing a workspace decomposition in order to guide a kinodynamic motion planner. So approaches like cyclop are going to give a lead path at every iteration of the planner from where you want to extend from that, or to from that configuration, reach the goal based on some information that we've encoded into this discrete abstraction, which is somehow talking about promising avenues of this continuous search. So our question was, can we somehow inform the multimodal planning search using a similar type of discrete structure to make search, be able to choose transitions better? 1 second, sorry. I haven't talked this much and I can feel my mouth drying out. Okay, so my contribution here is this multimodal planner that's guided by information that's gathered during planning, rather than this uninformed search or information that's computed offline. So at every iteration of the planner, what I was talking about, a candidate sequence of modes, not just mode families, is proposed to the planner. It's a sequence of not just what mode family to go to, but a sequence of mode families and specific parameters of the transition to try for each subsequent transition. So it attempts to find a plan between each of these transition points before failure. And then after it does that extension, it fails, algorithm repeats itself, chooses another node to extend from, rolls out the same procedure. And so this search is informed by maintaining a distribution of weights over the transverse parameters of each foliation, or each mode family. And what these weights do is they try to capture how difficult we estimate that motion planning into that transition point to be. And these weights are estimated online and are updated based on feedback within the algorithm as planning fails and succeeds, or as sampling transition points fail and succeed. All that information is included. And so moreover, because we're basing this multimodal planner on top of this general manifold constrained planning framework, we can handle anything or any system as long as the mode families can be modeled as these manifold constraints. So it makes it so that we don't need specific planners for anything. Everything can just be modeled and combined together using this framework. So how does it work? So here's a really simple example. We have this monkey robot with 2 limbs that can grasp some bars. The desired goal here is to get that monkey's torso to the base goal, that orange line up the top, get its torso somewhere in there. And on the left, you can see the transition graph for this problem. So let's say, let's look at one candidate transition. We're currently grasped to bar 1 with our right limb, and we want to swing up, grab bar 2 with our left. So as I said before, this method is going to build this distribution of weights over the transverse parameters of the mode family. So here I'm embedding them on top of the bar. And once again, that transition or these weights encode how difficult we think the problem is going to be. Obviously, and so this is actually generated from real data. You can see that where the obstacle is gets weighted way more heavily than other areas of the bar. And this is because we add penalties based on, like I said, if we try to find a transition point from, basically an intersection of these 2 mode families, if we fail to find a transition point in that area, we're going to heavily bias against it. If we succeed in planning, we don't bias it as heavily. But if we fail to do planning between one to the other, that's how we build these weights. And the assumption here is that we're going to be dealing with complex geometric problems. So we're going to be trying to constantly rolling out different transitions as we're trying to expand this planning graph. And note that the underlying assumption of continuity of the foliation is important here. When we add weight, we're not just adding weight at a specific point, we're adding weight kind of as a bump, with some attenuation based on the neighborhood of those parameters. Because we can say that planning problems at one parameterization of the foliation are going to be very similar to all the ones nearby. So we can add weight not just at that one specific point, but also to everything around it. So biasing search not just away from that one point, but away from that entire neighborhood of points or neighborhood of parameters in the foliation. Now, so this distribution is not just conditional on the, the destination foliation, is also conditional on where your source transverse coordinate is. And so we estimate these distributions in this joint space, shown on the left, x-axis here corresponding to the transverse parameter of your source mode family. The y-axis is the parameter of the destination mode family. And you can see here's like an example candidate transition shown highlighted, and kind of there's a configuration that would be, part of that intersection of these 2 mode families. Now, given that we have all these distributions that are being estimated, our method proposes the lowest cost candidate path to get to the goal based on these estimates to try and bias search. So this sequence then of desired transitions is then fed into the underlying single mode planner, where it tries to find single mode plans for each of these transition points, trying to reach the goal. And so that is a rough sketch of what this algorithm does. I'll stop here for any questions before I get into the experiments.
I actually have a question. So you showed the transition graph briefly on the left, right?
There you go. Yeah.
That one, is that one given as part of the problem specification?
Yes, it's given as part of the problem specification.
When you were talking about the task and motion planning methods, you were saying that they have the advantage that they can exploit the logic structure on the task level. Isn't that transition graph exactly that logic structure?
Yes. So that is kind of the what the insight of this approach is somehow trying to include that logical structure in order to bias the search. So it's still rather than, let's say, the prior approaches that have been done for the multimodal planning, where you have, you're either doing kind of informing based on single transitions or based on, basically local search from where you are, trying to bias it using this more global information that you have, similar to a task and motion planning approach.
And is the transition graph, does it have guarantees? So in a sense, in logic, there is a notion of sufficient symbols. meaning that they have refinement guarantees. So if you find like a symbolic plan, that you have a refinement guarantee to also find a geometric instance of that, which exactly arises that problem that you mentioned, that if the logic is not informed by the geometry, then that's almost impossible to guarantee. Is now this transition graph, does this have a refinement guarantee or not?
It doesn't need to, because we're doing this biasing of the weights. It will continue, like, so if you have, let's say, bum transitions available, like things like you said, there's not no refinement guarantee between this, like, for this transition in the graph. Because of how we're doing the weights, it eventually will stop searching that and bias along plans where it can actually find transitions. So we can handle that. Obviously, we don't, for these experiments, we don't have any experiments where we do that, but it can handle that. So for example, like, I can hand it a complete graph of transitions between everything. It makes it so that it performs very poorly, but it still will succeed eventually because we have probabilistic completeness guarantees.
Yeah. Just to mention, like some task motion planners like Kalins so have the same probabilistic completeness guarantees, right? And so their interaction between the, as you call it, between the logic and geometric level is really interesting in that they introduce many logic constants to represent feasible points. So anyway.
It's like, it's super, like the way that all these, like those planners do that, like the glue between the layers between, let's say, the domains is super, like, definitely we can talk about that later. Or, I find it super interesting how everybody does it.
Okay.
If nobody else has questions, I noticed that it's 9:53 here. I don't know how long this meeting's supposed to run, but I should probably get cruising.
Yeah, another 5 minutes would be good.
All right, I'll try and be fast. Okay. Okay, so for the experiments, I tested 3 variations of this algorithm. So we have uniform, which is the basic version of the algorithm. Basically, it's Hauser's work, but without offline information, just kind of uniform, basically chooses a transition at random, tries to resolve that. We have a variant called Dijkstra's, or I call it Dijkstra's, but this is a version that only gives a sequence of mode families to transition to. It doesn't have any information about the parameters to try along this foliation. So this gives a sequence of these mode families, and the planner just simply tries to transition to any point on that mode family, or to any mode from that mode family. It doesn't have any kind of, it doesn't care about what specific parameterization. And finally, we have augmented, which is all the bells and whistles. So it provides a sequence not just of these mode families, but also a specific segment of parameters to try to attempt to connect to. So, it could say like, hey, go to handrail 2 with, your left arm and try to grab it somewhere between like, the parameters 0.5, 0.6 or something like that. So it gives that sequence. So how does it perform? So here, this is this monkey robot climbing across an increasing sequence of bars. So we're increasing the total horizon of the plan that we need to be able to resolve. So here you can see that in this case, Dijkstra's actually outperforms the bells and whistles method because the parameterization of the bar isn't important. But you can see that it still outperforms the uniform method because providing the sequence of what things you need to try helps it out. Now, when the parameterization is important, or in the case where there's a ton of obstacles, learning these weight distributions is tremendously helpful. So here you can see that there's a ton of obstacles and a lot of challenging motion planning problems between grabbing each subsequent bar. And you can see that the weights learned by our method, so the augmented approach, really help the exploration of the planner to successful successful transitions. And finally, this method doesn't just work for monkey robots. It also works for any system you can model with manifold constraints. So here you can see this kind of complicated handoff scenario that requires grasp readjustment between each subsequent pass, complex geometric reasoning. And it's really similar to a lot of, like, let's say, task and motion planning problems, but our approach still is able to outperform baseline methods here. This weight information is important. So total, I presented this multimodal planning algorithm. It can solve, what I'm going to call these complex manipulation tasks. It leverages that manifold constraint planning framework so that we can do arbitrary systems. And the information that's learned on a line along with this discrete lead that's generated helps it solve both long horizon problems and also solve complex geometric problems more efficiently. Okay, before to the last section of the talk, I'll also pause here for some questions. Okay, So finally, so one of the main conceits that we have with this approach is that we're going to be trying a ton of different motion point inquiries, a ton of different individual manifold constrained motion point inquiries from one mode family, because that's how we're getting our weight information. And so these queries are all going to be very similar to each other. So, take the monkey example, you can think of, there's a couple of different problems that are all very similar to each other, where, there's just slight variations in the source and destination transverse parameter that we're looking at. You should think that solving one of these problems then kind of corresponds to having insight into how to solve the other. So one of the wrenches in the works here is that a problem that we're solving from one mode family lies on that underlying leaf manifold. And the solution paths from one are not going to necessarily apply to the other for any arbitrary, let's say foliation or constraint. And so the goal of this work was to figure out if we could somehow have the planner learn from experiences such that if you have a plan from one leaf manifold, you could transfer that experience to another close by leaf manifold. Broadly, the two types of experience-based methods that have been applied for multimodal planners and let's say task motion planners in general are ways of improving the underlying motion planning search. So if you recall, Konstantinos, he gave a talk at your group, I think a couple weeks ago at this point. So his methods all deal with how to do things like, under experience. I'm not going to really get into the details here, but the important thing here is that as far as I'm aware, there's not any method in the literature that explicitly handles the case of manifold constrained experience-based planning. Now, the other thing that you can do here is actually learn to bias your search based on what transitions you think are going to be good, based on things like human demonstrations, prior successful plans, but these don't necessarily improve the capabilities of the underlying motion planner. These just accelerate the discrete search element by providing good a priori guesses. So the contribution of this work, which just got accepted to IROS, is that we're going to propose a novel experience-based approach for planning under manifold constraints, explicitly those that are drawn from these foliated manifolds. So this framework can be used anywhere in any situation where you have multiple planning problems that are being constrained by leaves from that same foliation. It enables that experience to be transferred from one leaf to another leaf from that same foliation. And we use this in the context of the multimodal planner in order to accelerate planning in total. As the multimodal planner is going to, like I said, try all these different queries all from the same mode family. So the core of this method is leveraging that manifold, the manifold planning constrained framework earlier by building a sparse roadmap inside of a augmented space in which the foliation is a submanifold. And so we build connections inside of that space and then leverage that sparse roadmap in order to inform search later. And I'll talk about exactly how we do that in just a bit. And what's also nice is that this is kind of designed such that retrieval and training can be done online. So it can be trained over the course of a multimodal planning run. And I'll talk about a little bit about that later too as well. Okay, so how's it work? So first, here's that same two-link manipulator that I've shown before, maybe a little different of a color palette. But here you can see, here's that foliation, here's that manipulator mapping into the configuration space. Now we have this set of parameters X, and there, here there's like, one leaf manifold that's corresponding to the parameterization of chi. What we're doing is we're building a sparse roadmap inside the domain of the foliation shown here. You can see that there's edges and the nodes that are corresponding to their foliation parameter values, that color palette that is consistent between the two. Now this roadmap's not just within the configuration space. Like I said, the novelty of this method is the introduction of this augmented space, which includes not only the configuration parameters, but the foliation parameters as well. So here's that same roadmap now, rotating it out. It's the composite, the space, the 2D configuration space across this 1D parameter space in this case. And you can see how we're building this sparse roadmap on this submanifold inside this augmented space. Now here you can see the leaf manifold parameterized by chi, there's like a slice that kind of intersects through this augmented manifold here. Also, the edges aren't straight lines because they're geodesics on the manifold. Just want to make sure that's clear if that's confusing to anybody. So the goal of this work is we somehow produce this structure and then use this structure in order to inform search. So how's that work? So here's a sketch. So the axis on the left, really abstract representation. We have the set of parameters for the transverse manifold X. Here we have two plans here generated on leaf 1, another generated on leaf 2. we insert these plans into this augmented space and build this sparse roadmap according to, don't want to get into the details here. It's the SPARS algorithm, if you're familiar with it. What's nice about this is it has guaranteed sparseness and near optimality properties. So as we're building these connections, we're only considering the important connections that capture connectivity of the space. We don't add anything unnecessarily. There's a fixed point in which basically the sparse roadmap will consider itself complete, and we don't need to insert any more information. So every time we do a plan, we insert a leaf, or we insert the plans from these leaves into this sparse roadmap that exists inside this augmented space. Now, when you have a new planning request on a different leaf, that roadmap is then queried for relevant experience. So using the start configuration and a possible goal configuration from some goal region marked by the blue and the orange dots, a shortest path in that roadmap is found using a weighted metric of the configuration space and the foliation parameters. So this enables the return of paths that are close by the new leaf and parameter space, and thus are really likely to be able to satisfy that new constraint. So once you find that path inside the sparse roadmap, you can't use it as is because everything belongs to different leaves. And so the idea is that you then, squish all the, parameters from that you grab from the roadmap down using a projection method onto this new leaf. And every valid configuration is then used as a sample that is provided to the sampling-based planner to bias search. And so the way this works is that, under the hood, when you query for a sample with some probability, you try to query the underlying roadmap using some goal configuration that you have, get a path out from the roadmap, use those, squish it down, grab those as samples, accelerate search. I should have switched this slide as I talked about that. Anyway, so yeah, in summary, like I said, you're building this sparse roadmap, this augmented space. You query this roadmap every time you have a new planning query, and you use the paths from this roadmap, project them down to the new leaf, and use them to guide search as samples. So how does it work? So here's this similar monkey domain before. Each one of these bars is going to be with 100 trials. And note that the T-shaped obstacles here in this environment are varied between every run. They can move and rotate some small amount, including enough that the middle passageway that this robot's currently shown going through with the sweat volume, that actually goes away and it'll have to go around the outside. So we sample 100 different environments that we all trial these things in. And we have 5 different cases of the planner here. So one that is the baseline augmented method that I presented before, an adaptive method that actually learns online. So it starts with no information in the sparse roadmap, and it's trained purely as the multimodal planner progresses. Then we also have the framework that's trained on 10, 50, and then 100 plans. And you can see that as we add more and more experience into the data set, our planning time dramatically speeds up, even with just a very small amount of data. So that's for the monkey domain. And then here's an example with a similar kind of handoff environment. So here we're transferring the stick over, and that little spike obstacle can move up and down fully so that the spike's protruding and can rotate by 20 degrees or something like that. Sample, same kind of experimental setup. But you can see here that, once again, adding a small amount of data dramatically speeds up the performance of the planner. Okay, so to wrap this up, reusing experience in the constrained planning context now possible, and using that experience dramatically accelerates planning in these complex geometric examples. So it's fashion efficient, can be used online. Yeah, that's that. So I'll stop here for some questions.
So you mentioned that you every time moved around the obstacles, but the total number of obstacles stays the same.
Yes, the total number of obstacles in this case stays the same, yes.
So what would happen, or is it even possible to kind of change the environment more significantly by removing an obstacle or adding one?
Yes, so that is a limitation of these sparse roadmap methods, because what these roadmap methods really do is they kind of learn the invariance in the space. So, they really leverage the structure of, like I said, the invariant structure of the planning problem. So when you have dramatic changes in the obstacles or the environment, the experience that the sparse roadmap is able to learn becomes less and less relevant for the problem. And that's a known limitation of these kind of approaches. So once again, to hype up Konstantinos again from, a couple of weeks ago, his approach is directly designed around trying to address those kinds of limitations. Okay, let me finish up. All right, so talk a little bit about software. So brief advertisement. I don't know if anybody's really tried using ROS or Move It with anything to do with their research, but I personally found it absolutely confounding when I was trying to do more serious stuff like benchmarking or doing anything related to task and motion planning. So I developed Roboplex, which is this high-level API that wraps around Move It and makes it really easy to do motion planning for a lot of, let's say, research-oriented use cases. So things like benchmarking planners, evaluating, customizations to your planner, like, for example, cracking open the underlying OMPL implementation that Move It is using and then modifying that on the fly, adding your custom whatever to it, and then evaluating that in a benchmark, making that entire pipeline a lot easier to work with. I'm not going to go into any details, because of time, but it's available open source. Please give it a look if you ever have this kind of, if you find yourself needing to do anything like this. I put a lot of effort into the documentation. If you ever need to traverse into ROS land, give it a look. And some examples. So I have this extension that uses Dart, so you can do multi-robot motion planning a lot easier. You can copy and paste a bunch of different systems around. And also this really nice Blender visualization module that makes it easy to make really crisp visuals of motion plans. And that's what I use to generate that R2 figure at the beginning of the talk. Now, back to kind of the final motivating example. The end goal of this is to eventually apply multimodal planning to R2, to have it solve some complex manipulation tasks autonomously. So here's a couple of examples of tasks we'd like R2 to do. Turning valves, grasping these handrails, manipulating these bags out of these racks. And for example, here's a video that was taken a while ago with R2 climbing across this kind of mock-up ISS down here in Houston. You can kind of see that there's this like big gimbal thing on the back. This is like a zero gravity sim where it's actually offloading the weight of the robot, so you can have it move around kind of like it was in microgravity. But anyway, the point of this is you can see R2 was doing some interesting stuff like moving the torso with both feet attached to handrails, so doing this kind of in-place motion. It just turned the handrail here. It's about to slide this door along this linear rail. Now, the thing here is that all of these were kind of like a pre-specified sequence of motion plans. It's still using that underlying manifold constraint planning framework, but it's not doing the reasoning of what things to do autonomously. The hope was that I could this summer apply it to multimodal stuff to the Robonaut, but COVID obviously wasn't able to go down there, so that dream's left unresolved right now. But in the future, I really hope to be able to show this off, actually applying to R2 and solving these kinds of problems autonomously. And so it just manipulates the bag later. Anyway, so in conclusion, so what I've talked about here is this general framework for manifold constrained motion planning. It gives you theoretical guarantees. It's available open source. And this framework then is leveraged by this multimodal planner that has this, online search. It has this like synergy between the layers. So that you have informed discrete search that informs the continuous layer. And then eventually an augmentation of that such that you can have this experience-based acceleration of the underlying motion plan so that you can solve these kinds of problems faster. And in the future, like I said, want to apply these kinds of approaches to real robots, R2, expand the transition graph so it can handle things like PDDL domains and LTL specifications of tasks. And also, talk about getting into the theory a little bit more and talk about what guarantees we can get for multimodal planning in general. All right. Thanks everybody for listening, and thanks for having me.
Yeah, thank you.